Hello, everyone, and welcome to section 4.5, linear independence. Okay, our first example is going to show that the set of three vectors listed spans all of R2. Okay, so that means that we can write any vector in R2 as a linear combination of these three. So it'll look like C1 times 2, negative 1 plus C2 times 3, 2 plus C3 times 0, 1 is equal to any old generic vector in R2. So let's call it x comma y. Okay, reducing this down to a system, we can say this is 2C1 plus 3C2 plus 0C3 is equal to x, and minus C1 plus 2C2 plus C3 is equal to y. Therefore, we can write this as an augmented matrix, 2, 3, 0, x, negative 1, 2, 1, y. And we can begin row reducing, trying to show that this augmented matrix does not have a pivot in the augmented column. Okay, so what is this? How do we row reduce this? Let me get rid of this in the background. Let's go 2 times row 2, add it to row 1, and see what we get. So if this is negative 2, 2 plus negative 2 is 0. 3 plus 4 is going to be 7. And 0 plus 2 is going to be 2. And x plus 2y goes right here. And that's 2, 3, 0, x. And we can take the first row and divide by 2. 1, 3 halves, 0, x over 2. And 0, 1, 2 sevenths, and x plus 2y over 7. And you can see there's a pivot here, there's a pivot here, but more importantly, there's not a pivot there. So this is, and I know this is in row echelon form. It's not in reduced row echelon form. We need to take care of the 3 halves to make that work. But you can see that there's never going to be a pivot in the augmented column, and so this system will be consistent. It will have a solution. Okay. Now, to show that the vectors 2, negative 1, 3, 2 span R2, all we're going to do is take the same system, C1, 2, negative 1, plus C2, 3, 2, and instead of adding the third vector, 0, 1, just say xy. Wash, rinse, and repeat. 2, C1 plus 3, C2 is x, minus C1 plus 2, C2 is y. Create an augmented matrix. 2, 3, negative 1, 2, x and y. Do the very same row operation. Okay, 2 times row 2 plus row 1. 2 plus negative 2 is 0. 3 plus 4 is 7. X plus 2y. 2, 3x. Now we scale, and we say that 1, 3 halves, x over 2, 0, 1, x plus 2y over 7. Okay, we have a pivot in every column, and more importantly, there's not a pivot in the augmented column. I shouldn't say every column of the coefficient matrix, and not a pivot in the augmented column. Therefore, we have a consistent system, so solution exists. Therefore, the vectors 2, -1, and 3, 2 span R2. Okay, so if we're looking to find a spanning set for R2, the second set works. In other words, 0, 1 is redundant. It doesn't help us span R2. Okay, so you can see by the equation listed that 3 times the first vector minus 2 times the second vector plus 7 times the third vector equals 0. Okay, so you can write that as 3v1 minus 2v2 plus 7v3 is 0. And this tells you how any of the vectors in the linear combination can be written in terms of the other two. Okay, so if I wanted to say solve for, if I wanted to say, let's say, solve for v3, I could say 7v3 is equal to minus 3v1 plus 2v2, and v3 is minus 3v1 over 7 minus 3/7 v1 plus 2/7 v2. There you go. So you can see right here that v3 is a linear combination of v1 and v2, and thus is not needed in the set when looking at a vector that spans R2. So let's give you a definition. Okay. The set of vectors v1 through vn is linearly dependent if the equation v1 plus v2, c1 v1 plus c2 v2 all the way to cn vn equals 0 is true for some scalars that aren't all 0, so that are not all 0. However, a set is linearly independent if v1, c1 v1 plus c2 v2 all the way to cn vn equals 0, and this is the 0 vector, implies that all of the constants are equal to 0. So that means 0 can only be determined uniquely by making all the constants in the linear combination equal to 0. Linearly dependent means not all the constants have to be 0 for the linear combination to be 0. All right. So let's look at an example. Okay, you have this set of vectors, and you're asked, is this set of vectors linearly independent? Okay, so what are you being asked? C1 times 1, 1, 1 plus C2 times 1, negative 1, 1 plus C3 times 1, negative 3, 1 plus C4 times 3, 1, 2 equals 0. Okay, and the question that we have to answer when analyzing this is, must all the C sub i's be equal to 0? Okay, let's take a look. Rewriting this, okay, we can say that this is C1 plus C2 plus C3 plus 3C4 equals 0. C1 minus C2 minus 3C3 plus C4 equals 0. And C1 plus C2 plus C3 plus 2C4 is equal to 0. Okay. This obviously is a system of equations, so we can look at this as an augmented or as a matrix equation. So that's what 1, 1, 1, 3, 1, negative 1, negative 3, 1, 1, 1, 1, 2 times C1, C2, C3, C4 is equal to zeros, which now gives us our augmented matrix. 1, 1, 1, 3, dot, 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 0, 1, negative 1, negative 3, 1, 0, 1, 1, 1, 2, 0. All right. So now we're solving this system of equations with C1, C2, C3, and C4 as our unknowns. So let's row reduce. Okay, if we, let's leave row 1 alone, 1, 1, 1, 3, 0. Let's subtract row 1 and row 2 and make that our new row 2. So 1 minus 1 is 0, 1 minus a negative 1 is 2, 1 minus a negative 3 is 4, 3 minus 1 is 2, and no matter what I do to this side, you know, adding row 1, adding row 2, the augmented column is always going to be 0. Okay, so this will probably be the last example I really even care about the augmented column, because that's always going to be 0 no matter what combination I use. For row 3, let's replace row 3. Let's take row 1 and subtract row 3. Okay, so 1 minus 1 is 0, 0, 0, 1, 0. Okay, let's row reduced here. 1, 1, 1, 3, dot, 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 0, 0, 1, 2, 1, 0, 0, 0, 0, 1, 0. And one more time with pivot, pivot, pivot. Okay, put it in row reduced echelon form by getting rid of that. So 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 2 is negative 1, 3 minus 1 is 2, 0, 0, 1, 2, 1, 0, 0, 0, 0, 1, 0. Pivot, pivot, pivot. Okay, so there's no pivot in the augmented column. I know the system is consistent. I know that in the third column there isn't a pivot. So if we were looking at a solution, okay, we could say C1 minus C3 plus C4 is equal to 0. C2 minus 2C3 plus C4 is equal to 0, and C4 is equal to 0. I guess it's not row reduced echelon form because there's no zeros above that, so let's do that. If I subtract row 2 and row 3, 1 minus 0 is 1, 2 minus 0 is 2, 1 minus 1 is 0. So now I know that C4 is equal to 0, so that's a 0 right there. C4 is 0 right there. And if I subtract row 1 times 2 times row 3, I get 1 minus 0, 0, negative 1. 2 minus 2 is 0. So that's a 0 right there. So what do I have? I have C1 is equal to C3. I have C2 is equal to 2C3. I have, negative 2C3. This is a plus right there. I have C4 is equal to 0, and C3 is basically equal to itself. So this vector right here, the solution vector, can be written as scalars of the vector 1, negative 2, 1, 0. Okay, so let me explain how this is relevant. Okay. Well, actually, I'm going to do that in a couple examples from now. So is this set of vectors linearly independent? The answer is no. Okay, it's not, because if I let C3, there you go, be anything we want, like 1, Then C1 is 1, C2 is -2, C3 is 1, C4 is 0. I can say that 1 times the vector 1, 1, 1 minus 2 times the vector 1, -1, 1 plus 1 times the vector 1, -3, 1 plus 0 times the vector 3, 1, 2 is equal to the 0 vector. And so I found a way of obtaining the 0 vector with coefficients in this linear combination that are not all 0. There you go. Question answered. Next example. If W is equal to 3U minus 7V, show that the span of UV and W is equal to the span of U. Span of U and V. All right. So, to show that two sets are equal, what we'll do is we'll say, let some vector, call it Z, be an element of the span of U, V, and W, and show that Z is an element of the span of U and V. So, show that it's in this set, show that it's in this set. So, what does it mean to be in the span of U and V? That means Z is equal to some scalar, okay, call it, I don't know, D1 times U plus D2 times V. Okay, so ultimately that's what I want to show. So let's take a look at what I'm given. Z is a span in the span of U, V, and W. So that means Z is equal to C1U plus C2V plus C3W. Now W is equal to 3U minus 7V. By assumption. So that means C1U plus C2V plus 3C3U minus 7C3V is all equal to Z. Now reordering these and grouping them into like kind, you can see that I have a scalar times U plus a scalar times V. Okay, I can call this scalar D1, I can call this scalar D2, and then I would be of the form, I'd be of the form D1U plus D2V, which means that Z is really in the span of U and V. So that's half the battle. Okay, I've shown that every element in the span of U, V, and W is in the span of U and V. Now I have to do the other half. I have to say let Z be an element of the span of U and V. Show that Z is in the span of U, V, and W. Okay, so if Z is C1U plus C2V, what would happen if I added another vector, like W to the mix? Can I? Sure. Just multiply W by 0. Okay, so if I add 0W to this, okay, what I have is a vector that's from the span of U and V, but now is a linear combination of the vectors U, V, and W, so therefore is in the span of U, V, and W. So Z is now in the span of U, V, and W. Therefore, we've proven that the span of U, V, and W is the same as the span of U and V when W is a combination of U and V. So therefore, this set right here, the span of U, V, and W, can be pared down to the span of U and V because the vector W is dependent on the vectors U and V. Okay, there's that idea of linearly independent, dependent coming in again. Okay, because W depends on U and V, it doesn't make the span of U and V any larger by including W in it. Okay. All right. Example 3. Okay. In the example at the top of the page, we found that the set of vectors to be linearly dependent. Which vector can you delete from the set but still have the same span as the original? Does it matter which? Okay. So let's take a look. In our work for this problem, we found that there was a pivot in every column but one. Okay, the third column. Okay, that leads me to believe that the third vector can be a combination of the other two. Okay, let's see if I can demonstrate that. Okay, the first vector was 1, 1, 1. The second vector was 1, negative 1, 1. The fourth vector was 3, 1, and 2. And the third vector was negative 1, negative 1. Sorry, 1, negative 3, and 1. Can I write these three vectors as a linear combination that adds up to the third vector? I should. Okay, because remember we have this result here at the very end that says 1 times V1 minus 2 times V2 plus 1 times V3 plus 0 times V4 is equal to 0. So if we tack on to that, okay, we can get rid of this, that's 0. We can say that V3 is equal to minus V1 plus 2 V2. There you go. So we know now that V3 is a linear combination of the vectors V1 and V2. So when you look at the span of V1, V2, V3, and V4, you can say that's the same as the span of V1, V2, and V4, because V3 is dependent on vectors V1 and V2. So we're using the theorem that's just been proven that says whenever you have a vector in a list that's linearly dependent on the other two vectors, you can delete that vector from the list in your span and not affect the span of the remaining vectors. So because V3 is dependent on V1 and V2, we can delete it from our list and say that the span of V1, V2, and V4 is the same as the span of V1, V2, and V3 and V4. Very nice. And that all stems from this fact right here that there isn't a, I'm pointing at something you can't see. that there isn't a pivot in the third column. All the other vectors have corresponding pivots, and therefore are going to be relevant in determining the span of the set. Okay, but I will elaborate more on the second video, just so that this is not too long of a lecture all at once.